Simple harmonic motion and circular motion are linked. Circular motion looks like simple harmonic motion if you look at it side on. Take a paper plate and put a small blob of plasticine on its edge. Now spin the plate on your finger. If you look at the plate from above, you can see that the blob of plasticine is moving a circular path. Circular motion equations can describe the motion of the blob of plasticine when seen from above. Now I want you to look at the plate spinning, but only from the side and with one eye closed. Doing this should remove a lot of your perception of depth and allow you to see the blob of plasticine moving in one plane, backwards and forwards. This is simple harmonic motion. We are going to discuss how the graphs of motion look for simple harmonic motion. As discussed previously, displacement is zero at the equilibrium position. In our description above, this is the middle point of the edge of the plate. If we start our motion there, our real oscillator would never move. So instead, we start our motion at one edge of the plate and call this maximum positive displacement. Our plate is spinning with constant angular speed. This means that it moves around at a constant rate. When this happens, the blob of plasticine appears to move up and down, following a sinusoidal path. But because we have started at motion at maximum positive displacement, it actually follows a cosine path rather than a sine path. The displacement reduces from maximum, curving all the time so that it is steepest when it goes through the equilibrium position. After this point, the curvature of the line starts to decrease. The gradient of the line gets lower until it reaches the maximum negative displacement, where the gradient is zero. The line then moves back to the equilibrium position, again following the same curvature. Gradient increasing until it reaches the equilibrium position, and then decreasing again until it reaches the maximum positive displacement. This time, however, the gradient is positive, whereas before the gradient was negative. This is a description of the displacement time graph for simple harmonic motion. From previous studies, we know that velocity is displacement divided by time, or the gradient of a displacement time graph. In order to draw a velocity time graph for simple harmonic motion, all we have to do is plot the gradient of the displacement time graph against time. Initially, our displacement is maximum, but the gradient is zero. This means our velocity is zero. We put a velocity of zero for zero time. Our velocity time graph starts at zero rather than 1, like our displacement time graph, which started at 1. Following our displacement time graph, we see that the gradient increases in magnitude, but has a negative direction. The displacement is decreasing towards equilibrium. Our velocity time graph must therefore go downwards as well. The rate at which the velocity time graph changes is the same as the rate at which the displacement time graph changes. If our displacement time graph is a cosine, then our velocity time graph is a negative sine curve. It is like a sine curve but 180 degrees or pi radians further along. Where a normal sine curve would have a positive value, this negative sine curve has the same magnitude but a negative direction. We can summarise the key points of the velocity time graph compared to the displacement time graph. Both follow a trigonometric curve. Displacement starts at positive 1 and follows a cosine curve. Velocity starts at 0 and follows a negative sine curve. When displacement is at its maximum, velocity is 0. When displacement is 0, velocity is at its maximum. The direction of the velocity depends on the direction of the displacement. If the displacement is heading from positive to negative, then velocity is negative. If displacement is moving from negative to positive, then velocity is positive. We also know from previous study that acceleration is shown by velocity divided by time, which is the gradient of the velocity time graph. At time 0, when our plate starts spinning, or our oscillator starts bouncing, the displacement is at its maximum positive value. Velocity is 0, and about to increase negatively, and acceleration is at a maximum. Acceleration is at a maximum because the velocity time graph has got its largest gradient. As time moves forward, the gradient of velocity time decreases as the object is slowing down. The gradient starts off as a maximum negative value and eventually falls to 0. This means the acceleration does the same. The curvature of acceleration against time is the same type as displacement and velocity time graphs, trigonometrical. Whereas displacement time follows a cosine pattern and velocity follows a negative sine pattern, acceleration follows a negative cosine pattern. Where a cosine has a value of 1, a negative cosine has a value of -1, and vice versa. When displacement is at its maximum positive value, velocity is 0, going from positive to negative, and acceleration is at its maximum negative value. When displacement falls to 0 from positive, velocity is maximum negative, and acceleration is 0, going from negative to positive. When displacement is negative maximum, velocity is 0, going from negative to positive, and acceleration is maximum positive.